All right, so here we're talking about the 2D isoparametric element, and we're going to eventually talk about numerical integration. So here we're talking about a 4-node quadrilateral, and in fact, I think we've used this actually already in Abacus. This is the default it likes to try to mesh with. So it likes to try to do hexes and quads because they're more accurate. So we've already used this. A couple things you notice from the picture here. First one is that we're going counterclockwise still, so it's 1, 2, 3, and 4 for the numbering scheme. Again, that can be, you can actually go clockwise, although I have never seen it and I've never done it, but you'd have to change all your equations around that we present here. So I don't think you want to do that. Always go counterclockwise. We have, of course, the coordinates, the x and y coordinates, and so each node has 2 degrees of freedom, and that brings us to having a total of 8 degrees of freedom for this one element. Just as we did with 1D and 2D, you can consider some arbitrary point somewhere located in this element that you'd want to know for information for, right? You'd want to have a displacement, a u and a v displacement for that particular position. And just like we've done for previous elements, we want to define that sort of thing over the master element. Okay, so the master element, again, since we're in 2D, you can guess is using psi and eta as well as a natural coordinate, and it's going to be a square shape. So it goes from -1 down here, here's the master element, to all the way to 1, and so 0 is located right in the middle, and so that point now is a function of psi and eta. And so the shape functions, sometimes called the Lagrange shape functions, are defined in a similar way as previously. That is that at node 1, the shape function is equal to 1 and 0 at the other nodes, and goes like that all the way around. Here are actually the shape functions given. So it's a 1/4, and then you basically have 1 minus psi, 1 minus eta, or variations of plus and minus for each one of those shape functions. So that's the shape functions, 4 of them, 1 for each node. Now notice we have not actually defined how you compute psi. So for example, we had a way previously for 1D where we would map any position to a psi value, right? We haven't given that yet. We're going to talk about that in a later, but that does not actually exist easily for this 2D quad element. Let's assume that you have those shape functions. So let's assume we know what those are. It's easy then to use the values, the displacements at each of the node to compute the displacements, local displacement, including the shape functions. So you notice there we have n1 q1 plus n2 times q3, etc. Notice, just like in the constant strain triangle, we're skipping. So we're using the odd values because these are the x values, right? Remember, we have q1 is the x, q3 is the x, q5 is the x, and q7 is the x. So that's why you're seeing that here. And likewise, for the y displacement, we have the same thing, except we're using the even values. And of course, what's nice is we can write u is equal to nq, just like we just went over in the review for the problem. N, in order to do that, n has to be arranged something looks like this. So we have n with the other values equal to 0. Remember, in the isoparametric formulation, we use the same shape functions to express the coordinates of a point within the element in terms of nodal coordinates. One of the things we're going to need is a relationship between the natural coordinates and our typical x and y coordinates, okay? Because what happens is we have some integral, right, that we're going to do over, we're going to need the integral for both the stiffness, the forces, the tractions, etc. And that integral is over, if you remember, that's over the volume or the body, okay, of the continuum. So eventually what happens is we get down to a spot where we have the integral and we have a dx dy, right, representing the volume. And what we want to do is, because we're using isoparametric formulation, we want to actually represent that as d psi d eta on this master element. Okay, so one of the things that we're going to need to know in order to do that is the transformation between x and y and psi and eta. So you can see here, this is where our end result is, okay? But in order to get there, we have sort of a process. I have a couple slides, so I actually probably should have shown that equation first. But we start back here, and this is kind of what we talked about last time. This is the chain rule for derivatives, multi-derivatives. So we have this df d psi is equal to these terms, okay, some function of psi and eta, and we can represent that something like this. If we pull out the derivatives of x with respect to psi, okay, and so you have this Jacobian matrix, all right, and of course we could invert these if we wanted to, and we did that for the constant strain triangle. We also know that psi is equal to this and x is equal to this, so we can substitute these, sorry I said these, psi, this should actually be the shape functions n. We know x, and so we could substitute n's into these equations, okay. We then can take those derivatives, okay, because that will now give us x in terms of psi if we do that, and eta. So you end up getting j from here to there, substitute this stuff in, you end up getting j looks something like this. Okay, so you have 1 minus psi and x1, 1 minus eta times x1, 1 minus eta times x2, etc. You can see it here. We can represent each of these terms just as j11, j12. So we'll just simplify that to reference it. And then what we can do is go back to this equation and we can invert j. So we can do the inverse of j and then we can get df dx. Okay, df dx. Of course, j inverse is something like this. We know how to do that for a 2 by 2 matrix. And so we're left with dx dy is equal to determinant of j with d psi d eta as the what we can put in there. And this relationship here can then be used to create this transformation that we need. And we're going to need this in the derivation of the element stiffness matrix. And so we're actually going to talk about that in the next video.